In industrial settings, alkenes are prepared in quite a different fashion from that is used in lab. The reason for that comes that industry would preferably like to use the cheapest possible feedstocks for any process. In the case of alkenes, the cheapest possible imaginable feedstock would be alkanes, which are very abundant in petroleum. However, the problem with alkanes is their lack of reactivity unless we get to very forcing conditions. But that problem is easily overcome in industry because they are used to applying forcing conditions. And so the two processes that produce alkenes from alkanes cannot be used in normal laboratory settings, and we will not talk about them anymore, but I think it's important to familiarize yourselves with these industrial procedures as well. And so the first one we've already seen is called the catalytic cracking of alkanes. It is used in petroleum industry to convert long-chain alkanes into shorter-chain alkanes, and as a side product typically gives alkenes. And so this compound would be C12H26. It's a long-chain alkane, and as such is not very useful in gasoline. And so after cracking, we will get a shorter-chain alkane, the C6H14, and this is an alkane which is useful for gasoline industry, and the remainder of the molecule ends up as an alkene, C6H12. This process is performed on huge scales, and it produces alkenes, but is limited by its very purpose to production of alkenes of the order of several carbons, so for smaller alkenes. And it's also difficult oftentimes to control what kind of a mixture will we get in this process. And therefore it's useful, but only to a limited extent for production of smaller alkenes. Very careful distillation has to be applied to separate and obtain alkene from a mixture of other compounds involved. So it's again, it's not very useful process in academic chemistry. Another industrial possibility would be dehydrogenation of alkanes. And as the name implies, we would take an alkane and simply pluck off two hydrogens. This is under forcing conditions of heat to give us the CC double bond and H2 molecule. If you look at this system, what we notice is that we're breaking two CH bonds and forming a hydrogen-hydrogen bond, which is quite strong, but also we're forming a pi bond, which is relatively weak. And so if we actually add up these numbers, what we get is an enthalpy which is greater than 0. So this reaction is enthalpically unfavorable. The reason why this actually does occur lies in entropy, because delta G equals delta H minus T delta S, and delta G is the measure of whether our reaction will be spontaneous or not. Even though delta H is greater than 0, delta G still has a chance to be lower than 0 if T delta S becomes relatively large, and so delta H minus T delta S becomes lower than 0. And that's why T delta S needs to be large, and the way to control that is simply by controlling the temperature. So temperature is it needs to be high, and the reaction will perform at high temperature. The reason why change of entropy is positive in this case in the first place is that we go from one particle, molecule of an alkane, to two particles, molecule of an alkene, and a molecule of hydrogen. And these two particles can now roam freely and thus increase the disorder in the system. So, as a summary, industrially, alkenes, many alkenes are prepared from alkanes. This process is very difficult to control in lab, but in industry it can be achieved, and it typically requires very forcing conditions of temperature. Now, this will be all when it comes to new material for this lecture. But we will go now through two problems which show how concepts of mechanisms and synthetically useful reactions can be combined to solve a bit more complex problems in organic chemistry.